Okay, this is the second video in the Earth History unit on relative age notes. First part of the unit is comparing, or the relative age notes is comparing relative age to absolute age. Relative age is the age of something compared to something else. For example, I am old compared to you, which is young. It doesn't tell me my exact age, it just says compared to somebody else. You know, Mr. Modis is pretty dang old compared to his students. In contrast, the absolute age gives you the exact age of something. For example, Mr. Modis is 49, at least at the time of this video, and you're maybe 12, maybe 13. So absolute age is the real age of something. Relative age is the age of something compared to something else. Absolute age, we'll learn later in the unit, is determined by radioactive dating. And we do this with rocks and fossils, and we'll see how that works another day. This unit focused, or this part of the unit focuses on relative age, so save absolute age for later. So the first thing you have to understand about relative age is when you're looking at a layer or a section of cross-section of rocks is what they call the law of superposition. The law of superposition says that as layers were settled down in an area over time, they actually start from the bottom, and layers of ocean sediment and mountain eroding, they get piled on top of each other. So the layers at the top of any cross-section are going to be newer than the layers at the bottom. And that's actually referring to the law of superposition, which states that older rock layers are deeper in a cross-section of rocks. Another idea involved with how we understand that is called the principle of Uniformitarianism. It basically states that the processes of weathering, deposition, and erosion, which is how mountains are broken down and sediment is moved around on the surface of the earth, have always been pretty much the same. It's just an accepted idea that, hey, the speed of a mountain eroding from, if we had some mountain range over here, let's say, from the past, and all of its sediment that's coming and adding a new layer was the same as it was in the past, the speed of it, as it is today. And so the speed or the change on the earth is uniform. There's not a fast time and a slow time. It's always been the same. One of the things you have to understand or identify in unconformities is what in geologic cross-sections is what they call unconformities. And unconformities are areas where there's been erosion from some period of time when that area was on the surface of a geologic stack. And I didn't really draw a great unconformity in this geologic stack here, but it might be if I made this line a little bit more wavy, because I have these little pieces which we'll get to in a minute. And wavy lines represent that this layer that's kind of cross-section here has kind of been eroded away a little bit over time. Also in a geologic cross-section you can see what they call faults, which are breaks in the rocks that have been caused by an earthquake. This line right here would be the fault. And you see an offsetting of the layers. The layers have moved against each other, and that's how they identify that earthquakes happened and actually broken those layers apart from each other. Let me label this as an unconformity. Another piece that you have to know, again, we're determining the age of everything compared to everything else. And right now we're just learning how the terms are, but we'll eventually figure out how you interpret which happened first in this whole sequence. Another thing that we see in cross-sections are what they call intrusions, and that's when magma has actually melted its way up into a section of rock. So this right here, all the part right here would be an intrusion, which is now cooled and is solid rock from some point in the past. The mantle layer of the earth had actually just happened to melt up into this area right here. Maybe there was a crack in the rock, and so it was an easy way to kind of melt up and destroy this rock here, and you had a flow of this magma in here. This would be granite that formed when it cooled. If an intrusion actually makes it to the surface, and let's say this came out as kind of a volcano here and poured along the surface before these layers were formed, that part at the top there would be the next term here, which is called an extrusion. Layers that are formed by lava flow, it's when you have an intrusion that flows all the way to the surface. Now this extrusion has actually been covered up over time by the other layers that were put down, but at some point by the pattern of this kind of looking like it flowed out onto the surface when this crosshatch section was at the surface would point to that the intrusion made it all the way to the surface and made it extrusion. Other ideas involved with cross sections, as you have to know, is the principle of original horizontality. That states that sometimes in cross sections, and not this one here, you might have some folding of the layers are tilted or slanted. The principle of original horizontality states that all the layers of sedimentary layers were initially laid down horizontal, kind of as they are in this drawing right here. And that only from geologic uplift, plate tectonics moving, can you get some changes there. It's just an assumption we make about the layers, that they all start out horizontal until some other geologic process maybe changed them, like this crack has slightly moved those. An important idea in understanding the age of the different things in a cross-section is what is known as the principle of cross-cutting relationships. And what it says is any feature in a cross-section that's crossing over another one is, and this is the key idea, is younger than whatever it crosses over. It had to, for it to cross over something, that stuff had to be there already. Let's look at an example. In this cross-section here, this intrusion is an example of the principle of cross-cutting relationships. I'd say that it is younger than these layers that it actually melted through, because in order for it to melt through the layers, these layers had to be there. So when we're trying to figure out, what's new and what's older in a cross-section, understanding that if one thing crosses over something else, that has to be younger than the things it crosses. It's also true about this earthquake fault right here. In order for the earthquake fault to of breaking these rock layers, the rock layers had to be there. So the earthquake fault also demonstrates the principle of cross-cutting relationships, because we can say the fault is younger than the layers that it crosses. Finally, sometimes you see in layers what they call inclusions, and they're little rock fragments, which I tried to draw here, that are part of another layer. So when this crosshatch layer here was at the surface and these other layers didn't exist, it was weathering. That's why I had my little unconformity earlier, and there's some chunks, some rocks that were left on the surface. But then, say another ocean came in and sediment, this clear area of sediment came and was laid down, it filled in around these little chunks, so that now these chunks from this layer here have actually trapped in this layer above it. Those would be called inclusions, because they're included in one layer, but they actually came from another layer. Make sure you don't confuse the word inclusion with intrusion. They sound very similar, but they're definitely different. The last thing you have to understand when learning about relative age is how to tell the order of formation of events. And so from this cross-section, using the ideas that we've talked about, I'll just quickly number them. So starting with the oldest layer, using the law of superposition, the deeper I go, it's got to be older. This layer down here was the first one to come about. Then the second layer, this green one here, got laid down on top, so that was the next oldest. Then this layer, then this layer. Then you go, okay, well, I have this intrusion and I have this unconformity. I'm not sure if the intrusion that led to this volcano lava or this unconformity happened first. I'm going to have to guess in this case at the unconformity I had weathering away of the top of layer 4 here, and so I'm going to call that event 5. And then the intrusion came up. Just from the way that I drew it, I'm guessing that this spilled out over onto a weathering layer 4. So the intrusion, extrusion part would be, let's call it 6. And I know that this layer hadn't been laid down yet. For this to spill on top, this had to be younger than this layer right here. The next layer coming on top here had to happen before the earthquake. That would be 7, because the earthquake that made this fault actually broke this layer, and the principle of cross-cutting relationship says anything that crosses over something else has to be younger. So this layer has to be older. The fault has to be younger, which would be 8. And then we can see that there was a layer put on top of that, 9, then this layer, 10, 11. You can even add the stream to it. It cut into there as it eroded away those two. Those two layers had to be there in order for it to erode away. Again, that's the principle of cross-cutting relationships. So I could even go to 12. So that is the relative age of all the things in this picture, and we talked about the order that they formed. And that's it.